Alright, this is going to be a lecture video for chapter 15, all about fluids. So we'll talk about density, pressure, static equilibrium in fluids, pressure and depth, Archimedes' principle and buoyancy, application of Archimedes' principle, and fluid flow and continuity, along with Bernoulli's equation, applications of Bernoulli's equation, and viscosity and surface tension. So, first things first, we have to know the definition of density, which the density of a material is the mass per unit of volume. So density is represented by rho, which looks like a little p, and it's the mass of the object divided by the volume. For this class, it'll be measured in kilograms per meter cubed. Pressure is a measure of force per unit area. So P is going to be pressure, and it's going to be the force divided by the area, measured in newtons per meter squared. So if you have the same force applied over a smaller area, you're going to have a greater pressure. Okay, the smaller the area, the more pressure it's going to have. The example here is thinking of poking a balloon with your finger and then doing so with a thinner needle. You poke it with your finger, there's not going to be a lot of pressure and it probably will not pop because your finger is going over more area versus a thin needle doesn't have as much area that it covers. But if you apply the same force from your finger and to the needle is probably going to make the balloon pop because it's kind of more pressure because it covers so little area. We can also talk about atmospheric pressure. So you have the pressure that's due to the weight of the atmosphere above us. So there is a given for this, and it's typically 1.01 times 10 to the 5th Newton per meter squared. 1 Pascal is 1 Newton meter squared. So most of the time pressure is measured in pascals. That's kind of one of the other common units besides newtons per meter squared. So there's different ways to describe atmospheric pressure. In pascals, you would say it's 101 kilopascals. If you want to do pounds per inch squared, it's 14.7. You can measure in bars, so 10 to the 5th Pascal is 1 atmospheric pressure. So atmospheric pressure acts uniformly in all directions, so we usually don't notice it. So for example, if you want to add air to your tires, right, you do it to the manufacturer's specification, right? The inside of your door tells you how much to fill your tires to. You don't care about the total pressure. You are interested in is what's called the gauge pressure. So how much more pressure is there in the tire than in the atmosphere? So how much more do you need? So to get gauge pressure, take the overall pressure, so total pressure, minus the atmospheric pressure, and that's how much gauge pressure is left. Hence why they call it tire gauge. It doesn't take into account the atmospheric pressure, but just how much that the tire needs. So as an object is descending through a fluid, right? So think about if you have a block and you're pushing it down into a jar of water, because of the increasing mass of fluid that is now going above it, the pressure is going to increase, right? It makes sense. There's more water on top of the object versus just air. You're going to have more pressure on it at the top. So you can say that the force at the top of the fluid, right? So right now it's just being exposed to the air, is the atmospheric pressure times the area. versus at the bottom, the pressure is going to be the atmospheric pressure plus density times gravity times the height. So you were taking into account the atmospheric pressure plus everything else that is on top of it. And this equation here is the pressure with a certain density of the fluid. So atmospheric pressure, pressure due to the fluid. So add them together, you get the total pressure at the bottom of the fluid. So depth has an effect on pressure. So the deeper you go into a fluid, right, more depth, which means a higher pressure. All right, same equation as before. So if you wanted to compare the overall pressure at 2, which is down here towards the bottom, you would take the pressure at 0.1, which they have put here, and add the pressure due to the density of the fluid multiplied by the height. So then you get to real world examples, right? You have a barometer. It compares the pressure due to the atmosphere to the pressure due in a column of fluid, typically mercury. And this column of mercury has a vacuum above it where there's no pressure. So then the only pressure that's acting is the pressure due to the mercury. So then you can compare the two. So then you get another unit of pressure. If you did gas laws in chemistry, a lot of this is probably becoming very familiar again. So you have 1 atmosphere of pressure is 760 millimeters of mercury, mmHg. So in the barometer, the level of mercury is the pressure due to the column of mercury, and then that becomes equal to the atmospheric pressure. So it doesn't always have to be mercury. Any container where fluid can flow freely, the pressure is going to be the same throughout. So that's going to make your math a little bit easier. But you can see here you have water in the majority of these tubes and then oil. So the pressure is going to be the same throughout as long as the fluid can flow freely through it. We can go more into detail and call this Pascal's principle, which means that any external pressure applied to an enclosed fluid is transmitted unchanged to every point within the fluid. So kind of how a car lift works. You apply force on one side, then that pressure is going to add to the force that helps push up the car and make it lift. All right, Archimedes principle. So a fluid exerts a net upward force on any object it surrounds. This is called the buoyant force, right, FB. This force is due to the increased pressure at the bottom of the object as compared to the top. So buoyant force is the F2 force down here minus the F1 force up top here. Or you can write it as density of the object times gravity times the length cubed, right, if it's a perfect cube. You can also replace the equation as density of the fluid times gravity times the volume of the object, right? Not everything we use is going to be a perfect cube. So instead of doing length cubed, you just do the volume of the object. Whether it's a sphere, it's a cylinder, it's a rectangular prism, whatever is being submerged under the water. And then because it is a force, it's still measured in newtons. So some application of Archimedes' principle is that an object is going to float when it displaces an amount of fluid equal to its weight. So, like in A, some water is displaced here, but not enough to float the wood. But then once more water gets displaced, then the wood starts to float. So once the object displaces the water, the oil, whatever fluids it's in, enough to equal its weight, it's going to start floating. So an object that's denser than water can float only if it has indentations or little pockets of air that make the average density less than that of water. So if you have a block of wood and water equal weight, or a block of metal and water of equal weight, it's not really going to float as well. But then if you shape the object to where it has indentations or like a giant pocket of air, like a bowl, then it's able to float a lot easier. Less dense materials are going to float. So you can figure out how much of an object gets submerged as it's floating, right? Different objects have different ratios. You can find the submerged volume, so V sub, for a solid of volume and density floating in some sort of fluid. So you would do your volume of your solid object times the ratio of the density of the solid object versus the density of the fluid. And this would be measured in meters cubed because this is a volume. And this would be how much volume of your object is submerged underneath the fluid. Okay, fluid flow and continuity. So continuity tells us that whenever a mass of a fluid in a pipe passing a particular point per second, the same amount of mass must pass every other point in a second. So the fluid is not accumulating or vanishing along the way. All right, it's going to keep flowing. The liquid is not just going to disappear or hide anywhere. So where a pipe is narrower, the flow is actually going to be faster. Right? Think of playing with a hose. Right? If you just hold the hose straight out, the water's not going to go as fast. You put your thumb over it, then you're going to make it go really, really fast. So narrower the pipe, the faster the flow is going to be. All right, so there's an equation for this. You take the cross-section area of your two pipes or two cylinders, and you do the density at point 1 times the cross-sectional area times the velocity at point 1. And that is equal to the density at point 2 times the cross-section area of point 2 times the velocity at point 2. So they are equal to each other. It's going to compensate one way or other. Going along with this, you can compare it to gases too. So most gases we know are easily compressible. They can go anywhere, but liquids are not. Most of them aren't. So the density of a liquid can be treated as a constant, but not the same concept as a gas. So just know that they're similar as far as compressibility, but not. So if you have equation of continuity for an incompressible fluid, which is what most liquids are, cross-sectional area times the velocity at point 1 is equal to the cross-sectional area of point 2 times the velocity at point 2. When you move from a wider area to a narrower one, right, the speed's going to increase. We know the thinner in diameter the pipe is, the higher the velocity is going to be. But because of this, you can also calculate the work. Because this is happening, there is work being done. So you can calculate the total work done as the pressure of point 1 minus the pressure of point 2 times the change in volume. Bernoulli's equation. So Bernoulli's equation takes fluids and energy and kind of puts them all together. So you can calculate the kinetic energy of a fluid, right? Because if it's moving, it has kinetic energy. So 1/2 times the change in mass times velocity squared. You can rewrite that as 1/2 times the density times change in volume times velocity squared. If you set that equal to the work done, because if there's work being done, you have a change in kinetic energy, you can say that the pressure plus the 1/2 times density times velocity squared is equal to the pressure of the second point plus 1/2 times density of velocity squared. If you have fluid flowing in a pipe that has the same diameter, but it changes the height, work is also being done. It's just against the force of gravity, right? Think back to work and the change in potential energy, which relied on height. Same concepts here. So you can have the pressure at point 1 is equal to the density times gravity times height 1 is equal to the pressure at point 2 plus the density times gravity times the height at point 2. So it's relating the gravitational potential energy of the fluid based on the height of the pipes. So most generally, with height and speed changing, we can use that last equation for Bernoulli's equation for a constant speed. Right, as long as velocity isn't changing, you can use this guy. Essentially, he took the conservation of energy and applied it to fluids. That's what this equation is. So if you wanted to demonstrate and have an application of Bernoulli's effect, you would hold a piece of paper by the end where the hold the paper horizontally to where if it were stiff, right, have a good hold on it, blow across the top, the paper is going to rise due to a higher speed, but then that would also lower the pressure above the sheet. So more applications, this lower pressure with higher speeds is what rips off roofs off of houses in hurricanes and tornadoes and causes the roof of a convertible car to expand upward. But then on the biology side of it, this actually can help prairie dogs with air circulation. Right, they make all the tunnels, so if you have high speeds of wind, air, whatever, and lower pressure, it can help with the air circulation for them. Okay, this example is more common with Bernoulli's applications. So if you have a giant cylinder of water that has an open top, then at the top of the fluid, you have atmospheric pressure, right? It's exposed to the atmosphere. But then if you poke a hole on the side of this giant cylinder, then this hole in the very top up here is subject to the atmospheric pressure. So the pressure at the top is atmospheric pressure, and the pressure at the hole is also atmospheric pressure. Because the fluid inside the container is at the level of the hole is at a higher pressure, the fluid has a horizontal velocity as it exits. So this kind of goes back to kinematics a bit, calculation-wise. If the fluid is directed upwards instead, then it's going to reach the height of the surface level of the fluid in the container. So if the water level is up here, then when it comes out this opening here, it's going to reach that same height. Viscosity. So viscosity is a type of friction for fluids. mostly we've been dealing with non-viscous fluids, no friction, but in the real world, fluids will have some viscosity. A viscous fluid will have zero velocity next to the walls, and the maximum velocity will be at the center. Okay, so picture A is in the perfect world. Picture B, this is the real world. This is what it's actually going to do. So it takes a certain amount of force to maintain a viscous flow, just like it takes a certain amount of force to maintain motion when you have friction, right, to keep it going. A fluid is characterized by a coefficient of viscosity, just like you have a coefficient of friction, you have a coefficient of viscosity, and that's this little guy here. Looks like a lowercase n, but it's defined so that the pressure difference in the fluid is given by this equation here. So the pressure at point 1 minus pressure at point 2 is equal to 8 pi times the viscosity constant, or not constant, coefficient, times the velocity, times the length divided by the area. You can use this to help you calculate the volume flow rate with viscosity. So change in volume over change in time is equal to the velocity of the fluid times the cross-sectional area. Rearranging a bit from the equation we had on the last slide, you get this equation to calculate the volume flow rate. So when you have a drop of liquid, it experiences forces in all directions from other molecules. A molecule that's on the surface, however, is going to experience a net force toward the interior of the drop. It's going to pull the surface inward so that the area here is going to be a minimum. So since there are forces that tend to keep the surface area at a minimum, it kind of acts like a little spring. So the drop is kind of elastic in a way. It's bouncy. So this means that small dense objects such as insects, right, certain kind of spiders, too, and needles can stay on top of water even though they are too dense to float. You learn a lot about this in bio if you take it too. Cohesion, adhesion of water molecules, but surface tension is kind of just bonus information for us. So if you are ever curious, you can do more research on it.